As we continue with our discussion regarding series, what we have now, once we have the basic idea of what a sequence is, and then the series that we get from those sequences, now we have a collection of what are called tests for convergence. The key thing, the key notion for a series is whether or not it converges. Let's just take a little quick look there. Remember, a series converges if the sum is a finite value. If the sum is not a finite value, then it diverges. Now, there are a couple ways that diverging can happen. Diverging can be the sum never actually accumulates to a specific point. That is to say, the value oscillates between two points. So an example of that might be something like this. If we have negative 1 to the n times, let's say, 2. Well, that sum, when n equals 1, this is negative 2. And then when n equals 2, this is the squares. Negative 1 squared is 1, so this is 2. And then when when n is 3, this is negative 2 again. So this is an alternating series. Remember, that alternates between positive and negative. And that continues. And look at the partial sums. Sum number 1 is negative 2. Sum number 2 is negative 2 plus 2, which is 0. Sum number 3 is negative 2 plus 2, which we just had, but then you subtract off the next piece. Term number 1, term number 2, term number 3, subtract off the next 2. This is negative 2. And it's not very hard to see that this sequence of partial sums oscillates back and forth between negative 2 and 0. And so that sequence of partial sums continues to oscillate back and forth. It never reaches us one single specific value. So the sequence of partial sums oscillates between negative 2 and 0. And so that sum doesn't exist, or that sequence does not have a limit. And so this sum has no value. So this is an example of something that diverges. Converges if the sum is a finite value. This diverges because this does not achieve a finite value. Another way for a series to diverge, and this is probably maybe a little more common, something like this. The sum as n goes from 1 to infinity of something simple like 2n. Well, what does that correspond to? This, when n is 1, this is 2 plus 4 plus 6 plus 8 plus 10 plus and so on. It should be very clear that sequence, when you add together, for one thing, the terms themselves go off to infinity, and when we add them all together, it is clear this is not going to equal any finite value. For example, suppose someone says this actually does converge, and you pick any finite value you would care to pick. Suppose someone says, I believe this actually adds up to 1,000. Well, we know that's not correct, because eventually one of these numbers, and eventually all of these numbers, get larger than 1,000. So no matter what finite number you would suggest that the sum actually equals, eventually the terms of this series get larger than that number, and so the sum exceeds that. This sum goes off to infinity, and so that, again, this does not meet the condition for convergence. An example of a series that does converge is a geometric series where the value of r, absolute value of r, is less than 1. If we take 2 times 1/3 to the n, this is a geometric series. A equals 2, r equals 1/3. So we have absolute value of r which is absolute value of 1/3. That is less than 1. And so therefore this does converge. That is to say, this sum adds up to a finite number. Now remember, for our work, if a series is geometric, or if the series is telescoping. A telescoping or a geometric series if they do converge, we actually can find the sum. It turns out for our work, as a general statement, those are the only two sums we can actually find. But in this case, we actually can find the sum. We know that that sum, and sometimes occasionally we'll just call this the sum. The sum is equal to this expression. We know this is A over 1 minus R, which in this particular case is 2 over 1 minus 1/3, which is 2 over 2/3. And if you multiply by the reciprocal, I believe that the 2's cancel, that simplifies to 3. All those terms add up to 3. If we expand this out, this would be 2 plus 2/3 plus 2/9 plus 2/27 plus and so on. What does that add up to? That adds up to 3. Not approximately, precisely 3. And so if the series converges, if the sum is finite. So if this sum is a finite value, the series converges. Usually, in fact, the overwhelming majority of series that we're going to be discussing that are of interest for us are not going to be geometric series. They're not going to be telescoping series. So very often we cannot actually find the sum. However, it turns out for our work we don't need to find the actual number. All we need to know is whether or not the series converges. And to that end, we have a collection of what are called tests for convergence. There's a series, and we don't know whether it converges or not. So we apply a test. It's rather like a litmus test. You take the litmus paper and you investigate the liquid to see if it's acid or base. In this case, we apply a particular mathematical theorem or procedure, and either the series converges or it doesn't. And so that's the approach we're going to take. There are a collection of tests for convergence, and that's what we're going to be discussing now. So, now, it should also be borne in mind, some of these tests are, they tend to fall into two categories. One category is primarily, not exclusively, but primarily as a theoretical stepping stone to get to a different result. An example of that is the direct comparison test when we talk about it later on. Yes, it does work, and it does have a certain body of functions where a series where it can actually work. However, it is an example of a test which is a legitimate test, but it is primarily a stepping stone to get to something else, a theoretical stepping stone to get somewhere else. Others, the second category, are the ones that are actually practically, in a pragmatic sense, very useful. The ones that you actually tend to use over and over and over. So we'll take a look at these and get some practice working with them. So the first of our tests for convergence is called the integral test. All right. Integral test says this. Given a series, if f of x is the associated function for an, the sequence an. Now, what does that mean? F of x is the associated function if the terms of the series agree with the function value. And so the idea is the first term actually does equal f of 1. And the second term actually does equal f of 2. And so the terms of the series are actually values in the range of the function for those specific numbers. And we would call something like this. So if we had n equals 1 to infinity, very often we could have something like this. N over n plus 1 is a standard example. This is a series. The associated function for that would be x over x plus 1. The advantage in this particular case is L'Hopital's rule does apply here because this is a continuous function. L'Hopital's rule does not apply here because this is discrete. It's not continuous. And so when we say, in order to apply the integral test, we need to assume that we actually have the what I'm calling the associated function. Right, so we have the associated function, and there are a couple conditions that must be met. In order to apply the integral test, we must ensure that the series meets the requirements for the application. And the requirement is this, is that f is positive, right? Is positive. Now, what does that mean? It must, all the function values they cannot be negative, they cannot be zero. Remember, there are three categories of numbers: the negatives, zero, and positive. Zero is not a positive number. Zero is neither positive nor negative. So when we say f is positive, what that means is all the terms of the series and all the values of the function, nothing can be negative, nothing can be zero. They're all positive values. F is positive, continuous, and for our purposes, that condition will be met. And here's the key: decreasing. It's got to be positive, continuous, and decreasing. One of the simplest ways for the basic kinds of things that we will encounter to ensure that this function is decreasing is to take the first derivative and show that the first derivative is always negative. That suffices to show that the function is decreasing. So if that's the case, if the associated function is positive, continuous, and decreasing, then either both converge or both diverge. Either they agree on this converges as a series if and only if this converges as an integral, and this diverges as a series if and only if this diverges as an integral. So if you want to determine whether or not this converges as a series, switch to the function, compute this improper integral. If that converges, if that gives you a finite value, then so does this, and vice versa. And so if this does not converge, then that guarantees this does not converge. Now, as a practical matter, the integral test doesn't get used very much for the work that we will encounter. Occasionally, a series will have terms involving logarithms. And one of the convenient ways to work with series involving logarithms is to switch to the associated function, the natural log function, and then work with the function rather than the series because you have continuity working for you. That's probably the most common use at our level of study. But this is the big piece. The big piece for the integral test, and I will say this, for our work, there are going to be no series where you will require using the integral test. If someone makes up a problem that at this level of study that requires you to use the integral test, the reason that it happens is because they have made up a problem that requires for you to use the integral test. The primary use of the integral test is this. In fact, you'll notice I'm not even going to illustrate it here. Is to get to the notion of a p-series. So I wanted to define a p-series. A p-series is any series in the form one over n raised to the p power, and we assume that p is greater than 0. We assume p is positive. If p is negative, then this is a negative exponent. You move up to the numerator and forget about the fraction. So this is a p series. So examples of p series. N equals 1 to infinity, 1 over n to the third. That's a p series with p equal to 3. Sum n goes from 1 to infinity, 1 over the square root of n, because this is n to the 1/2. That's a p series with p equals 1/2. 1 over n to the 1/2 power. 1 over n to the 5th. That's a p series with n equals 5. And there's one in particular, 1 over n to the 1st. 1 over n to the 1st is a p series. And this has a special name. This one has some special properties. This has a special name. This is called the Harmonic Series. It actually has application working with the harmonies in the musical scale. For our purposes, it's simply called the Harmonic Series, 1 over n. All right, so a p series is any series in the form, the sum 1 to infinity of 1 over n to the p power, where p is bigger than 0. Now, the question is, when do they converge? All right. Well, notice that the associated function for this series is the function 1 over x to the p. And the integral test, it says we can investigate. This does meet the qualifications. This is continuous. It is positive. All the values are positive, and and it is decreasing. Right? These are the functions: 1 over n squared, 1 over n to the 5th. All these are these decreasing hyperbolic functions, or functions whose graph is hyperbola. And so if we investigate this integral, this is an example, back when we were talking about, in the previous chapters, when we were talking about improper integrals. One of the reasons we talked about improper integrals was to introduce this notion of a p integral. And a p integral, one of our results from that section is, this converges if and only if value of p is bigger than 1. It diverges if 0 is less than p is less than or equal to 1. Remember, p is not allowed to equal 0. And so here it is. If we want to find how 1 over n to the 3rd behaves, we investigate 1 over x to the 3rd. But then we would use the integral test, and we would switch to 1 over x to the 3rd. But that is a p integral, and we've already established that. This integral converges for values of p bigger than 1. It diverges for values of p between 0 and 1, or if p is equal to 1. And so by the integral test, we can make the same conclusion over here. If this integral converges only for these values and diverges for these values, then we may also say that a p series converges if and only if p is bigger than 1. A p series diverges if p is between 0 and 1 or equal to 1. And so we know immediately from those results, we know immediately that this series converges. It is a p series with p bigger than 1. This converges. This is a p series with p less than 1. This series diverges. This is a p series with p bigger than 1. This series converges. This is a p series with p equal to 1. The harmonic series diverges. This series diverges. 1 plus 1/2 plus 1/3 plus, and so on. That series diverges. The sum is infinite. It is perhaps worth noting here, this goes off to infinity. It just takes a really, really long time to get there. I actually did some work this morning. It turns out to make this sum goes off, it's clearly bigger than 1, because 1 plus 1/2 is bigger than 1. It's not quite so obvious, but it is in fact bigger than 2. But this does get big. This gets bigger than 10 eventually. This gets bigger than 15 eventually. However, it takes its own sweet time because the further out you go, the less you're adding. It turns out that in order to get bigger than 15, you need to add over 1,000,000 terms. The first 1,000,000 terms don't even add up to 15. Although if you add them all out to infinity, it does go off to infinity. And I looked this up. In order to get bigger than 50, you need to add the first something like 5 sextillion terms in order to get it bigger than 50. So it takes a long time for it to get very big, but it does, in fact, eventually get larger than any specific value. So all that's wonderful and great to discuss, but for our purposes, the big takeaway here is this: a p-series. And the only real place we're using the integral test is as the theoretical stepping stone to get to this result. A p-series converges if p is bigger than 1. A p-series diverges if 0 less than p less than or equal to 1. If p is between 0 and 1 or equal to 1, the p-series diverges. If p is greater than 1, the p-series converges. So now, any p-series, you should be able to look at it and tell whether it converges or not. This series is a p-series with p bigger than 1. This converges. We do not know what the sum is, but we do know that if you add those up, it's a finite number. This diverges. This converges. We don't know what the sum is, but it converges. It's a p-series with p bigger than 1. This series diverges. It's a p-series with p equal to 1. The harmonic series diverges. So that's really all the use to which we're going to put the integral test primarily. It is rare at this level of study that the integral test would be the kind of thing required to illustrate convergence for a series. The big takeaway for us is the notion of the p-series. P-series converge if p is greater than 1.